March 14, 1944. Lieutenant Commander John Blackburn was pulling 7 Gs in a screaming dive over Rabaul Harbour when his throttle hand did something that should have killed him. 22,000 feet above the Solomon Sea, chasing a Mitsubishi A6M Zero that had just put 3 7.7mm rounds through his starboard wing, Blackburn's F4U Corsair was approaching 410 miles per hour in a 70-degree dive. The airspeed indicator was winding up like a clock spring. The control stick was getting mushy as compressibility effects started playing games with the airflow over his wings. And the Zero ahead of him was doing something impossible. It was pulling out. Not gently, not gradually. The Japanese pilot was hauling back on his stick in a desperate emergency recovery, trading every ounce of airspeed for altitude, trying to avoid slamming into the ocean at terminal velocity. And his aircraft was responding. The Zero's lightweight airframe, stressed for 6 Gs maximum, was bending under the load but holding together. The dive angle decreased from vertical to 60 degrees to 45 to level flight at 8,000 feet. The Zero leveled off, still flying, still fighting, while Blackburn's Corsair was still pointed at the water with the airspeed indicator showing 420 miles per hour and climbing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Blackburn knew the math. He'd been briefed on it 3 times during training at North Island. A Corsair pulling out from a high-speed dive needed altitude. Lots of altitude. The heavier the aircraft, the wider the recovery arc. At 400 miles per hour, his pull-out would require at least 3,000 feet of vertical space. He was at 8,000 feet. He had room. Barely. But something in his gut, said the Zero, shouldn't have been able to pull out at all. The intelligence reports were explicit. Japanese fighters were lightly built. They traded armor and structural strength for maneuverability. At high speeds, that trade-off became fatal. Zeros weren't supposed to survive dives above 400 miles per hour. The wings were supposed to fold. The airframe was supposed to compress. Pilots were supposed to black out from the G-forces before their aircraft could recover. Yet this Zero had just done exactly what it wasn't supposed to do. And Blackburn was about to find out why the official intelligence assessments were dangerously, fatally wrong about Japanese aircraft structural limits. The Pacific War in early 1944 had settled into a brutal pattern. American industry was flooding the theater with aircraft, ships, and supplies that Japan couldn't match. But Japanese pilots were still dangerous. They'd learned hard lessons during 2 years of combat. The Zero might be outclassed by newer American fighters in raw performance, but it remained lethal in the hands of experienced pilots who understood its strengths and could exploit American overconfidence. That overconfidence centered on dive performance. Every American fighter pilot in the Pacific had been taught the same tactical gospel. If a Zero got on your tail, dive. The Corsair, the Hellcat, even the older Wildcat, all had superior dive performance. Japanese fighters couldn't follow you down without risking structural failure. It was written in every tactical manual, repeated in every pre-flight brief, verified by captured aircraft testing at Wright Field in Ohio. The captured Zero that changed everything had been found in the Aleutians in July 1942. A Mitsubishi A6M flown by Petty Officer Tadayoshi Koga had crash-landed on Akutan Island after taking combat damage during the Dutch harbour raid. The aircraft had flipped inverted in soft tundra, killing Koga but leaving the Zero, remarkably intact. American forces recovered it a month later, shipped it to San Diego, and spent 6 months rebuilding it for flight testing. The flight test program at North Island ran from September 1942 through January 1943. Test pilots from the Navy and Marines flew the captured Zero through its entire performance envelope. They documented its incredible maneuverability, its tight turning radius, its docile handling at low speeds. They also documented what they thought were its structural limitations. During high-speed dive tests, the Zero showed alarming characteristics above 350 miles per hour. The controls became extremely heavy. The aircraft developed a violent nose-down tendency. Recovery required significant physical strength. At 400 miles per hour indicated, The control forces were so extreme that test pilots reported they could barely move the stick. The conclusion seemed obvious. The Zero's lightweight, construction couldn't handle high-speed flight. American aircraft with heavier, more robust airframes could dive faster and pull out more aggressively. This became doctrine. Dive performance became the American trump card in Pacific air combat. If you got in trouble, point the nose down, firewall the throttle, and leave the Japanese behind in your wake. But the test pilots at North Island had missed something critical. They'd tested a Zero that had crash-landed in soft tundra. The impact had been gentle enough to leave the airframe mostly intact, but violent enough to subtly distort the fuselage structure. The Zero they tested wasn't exactly factory fresh. More importantly, they'd tested it in a specific configuration, without drop tanks, without ammunition, at weights lighter than combat-loaded aircraft. And they'd tested it using American dive techniques, steep angles with aggressive throttle application, not the dive profiles Japanese pilots actually used in combat. Japanese naval aviators had developed dive tactics specifically designed around the Zero's characteristics. They didn't dive vertically. They entered shallow dives, typically 30 to 45 degrees, that built speed gradually while maintaining control authority. They reduced throttle during the dive to keep engine RPM within limits and prevent overspeeding the propeller. And they initiated recovery earlier, while still maintaining sufficient control effectiveness to pull out smoothly without overstressing the airframe. These techniques weren't secrets. They were standard training procedures taught at Tsuchiura and Omura flight schools, but American intelligence had never captured a Japanese tactical manual that explained them. The assumption was that Japanese dive limitations were structural, not procedural. That assumption was killing American pilots who thought they were safe once they pointed their nose down. Blackburn's Corsair had an advantage the Zero couldn't match in level flight or climbs. The Pratt & Whitney R2800 double Wasp engine generated 2,000 horsepower, nearly double the output of the Zero's Nakajima Sakai engine. In a straight race, the Corsair was 40 miles per hour faster. In a climb, it could outpace the Zero above 15,000 feet. But in a dive, weight became the defining variable, and that's where American understanding of Japanese aircraft became dangerously incomplete. The F4U Corsair weighed 12,570 pounds, fully loaded for combat. That included pilot ammunition for 6 50 caliber machine guns, full internal fuel, and armor plating behind the cockpit. The Zero weighed 6,000 pounds fully loaded, less than half the Corsair's combat weight. In a dive, gravity accelerated both aircraft toward terminal velocity, but the heavier aircraft reached higher speeds more quickly. Basic physics suggested the Corsair should outdive the Zero by a massive margin, and it did, until both aircraft approached their structural limits. Then something unexpected happened. The Corsair's advantage evaporated because both aircraft were hitting the same wall, just from different directions. That wall was called compressibility, and in 1944, most pilots barely understood it. Compressibility occurs when an aircraft approaches the speed of sound. Air molecules can't move out of the way fast enough. They compress into shock waves that disrupt airflow over the wings and control surfaces. The aircraft stops responding to control inputs the way it should. The dive angle steepens uncontrollably. Recovery becomes difficult, then dangerous, then impossible. The speed of sound varies with temperature and altitude. At sea level in standard conditions, it's approximately 761 miles per hour. At 20,000 feet where the air is colder, it drops to about 660 miles per hour. Compressibility effects begin appearing well before an aircraft reaches the sound barrier, typically around 75 to 80% of Mach 1. For aircraft diving from altitude, that meant trouble started around 490 to 520 miles per hour, depending on temperature and pressure. Both the Corsair and the Zero could approach those speeds in a dive. The Corsair got there faster because it was heavier, but both aircraft entered the compressibility regime if the pilot held the dive long enough. And once they entered that regime, structural strength mattered less than aerodynamic design. The Zero's controls became heavy because its control surfaces were encountering compressibility effects. The Corsairs' controls became heavy for exactly the same reason. Neither aircraft was designed to operate efficiently in transonic airflow. The critical difference was recovery technique. American pilots had been trained to maintain full power during dives. The logic was simple: more speed equals more separation from pursuing enemy aircraft. But full power at high dive speeds created problems. The propeller was spinning at maximum RPM, generating enormous drag as the blade tips approached supersonic velocities. The engine was producing thrust, but at 400 miles per hour, propeller efficiency collapsed. Instead of pulling the aircraft through the air cleanly, the propeller was churning through compressed air and generating turbulence that disrupted airflow over the entire fuselage. Japanese pilots had learned through brutal trial and error that reducing throttle during high-speed dives improved control response and made recovery easier. Less engine power meant lower propeller RPM, which meant cleaner airflow, which meant better control surface effectiveness. They could pull out at higher speeds with less altitude loss because their aircraft was aerodynamically cleaner during the recovery phase. American intelligence knew none of this. The tactical assumption remained that Zeros couldn't survive high-speed dives, and that assumption kept getting pilots killed when they discovered, too late, that the Zero chasing them could absolutely follow them down and might actually recover first. Blackburn was learning this lesson at 8,000 feet over Rabaul Harbour on March 14, 1944, with his airspeed indicator showing 435 miles per hour and his dive angle still too steep to survive impact with the ocean. His Corsair's propeller was screaming at 2,700 RPM. The Pratt & Whitney was bellowing at war emergency power, and his control stick felt like it was set in concrete. He pulled back with both hands. The stick moved maybe half an inch. The dive angle decreased maybe 1 degree. He needed 30 degrees of pitch change to level off. He had altitude for maybe 8 seconds more of descent. His right hand was wrapped around the throttle quadrant, knuckles white inside his leather glove, when muscle, memory from a completely different aircraft, made him do something he'd been explicitly trained never to do in a high-speed dive. He pulled the throttle back to idle. Not partially. All the way. The Pratt & Whitney's roar dropped to a low growl. Manifold pressure collapsed from 64 inches to 28. Propeller RPM decreased from 2,700 to 1,800, and something impossible happened. The control stick lightened. Not dramatically, but noticeably. Blackburn pulled again, this time with pressure he could actually manage. The nose started coming up. The dive angle decreased from 60 degrees to 50, to 40, to 30. At 2,000 feet above the Solomon Sea, his Corsair shuddered through level flight, still carrying 420 miles per hour, but flying level instead of diving into the ocean. Blackburn's first conscious thought was that he'd just survived by accidentally doing the exact opposite of what every tactical manual recommended. His second thought was that he needed to figure out why it worked before he forgot what he'd done. His third thought was that the Zero had gotten away. He climbed back to 12,000 feet, checked his fuel state, and headed northwest toward Treasury Islands, where VMF 215 was operating from a forward strip. The flight took 38 minutes. Blackburn spent most of it trying to reconstruct exactly what had happened. He'd been at 8,000 feet, doing 435 miles per hour, dive angle too steep to recover. He'd pulled the throttle to idle. The engine power dropped, the propeller slowed down, and suddenly his controls worked again. The sequence made no aerodynamic sense based on what he'd been taught. Reducing power should have meant less energy available for maneuvering. The aircraft should have been harder to control, not easier, unless the power itself was the problem. Unless at high speeds, the propeller and engine thrust were creating more drag and turbulence than useful force. Unless everything the Navy had taught him about dive recovery was optimized for normal flight conditions, not for the transonic chaos that happened when you pushed a propeller-driven aircraft past 400 miles per hour in a screaming dive toward the ocean. He landed at Treasury at 1410 hours, taxied to the maintenance area, and climbed out looking for the squadron's engineering officer. Lieutenant Carl Morrison was a former mechanical engineering student from MIT who'd left school in 1942 to join the Navy, and had somehow ended up as the technical expert for a marine fighter squadron instead of designing ships in a Portsmouth office. Blackburn found him inspecting a Corsair with a shredded aileron and a story that started with, "So there I was." "I need to show you something," Blackburn said. "It's about dive recovery, and I think I just broke every rule in the flight manual and saved my life doing it." Morrison listened while Blackburn explained the dive, the throttle reduction, the sudden improvement in control response. Morrison's expression shifted from polite interest to focused attention when Blackburn described the control stick pressure decreasing after he'd cut engine power. "Propeller drag," Morrison said. "At high RPM in dense air, the prop is generating massive drag. You cut the throttle, RPM drops, drag decreases, airflow smooths out. Makes sense, but nobody's tested it because the manuals say never reduce power in a dive." He paused. "Did you try this more than once?" "Once was enough," Blackburn said. "I was about 4 seconds from dying when I did it. I'm not eager to test it again for science." "But it worked." "It worked." Morrison looked at the Corsair Blackburn had just parked, then looked back at Blackburn. "If this is real, if cutting throttle actually improves high-speed dive recovery, we need to test it properly. Because if you're right, every pilot in the Pacific is diving wrong. And the tactical manual that's supposed to keep us alive is actually making dives more dangerous. How do we test it without killing someone?" Blackburn asked. "Carefully," Morrison said. "Very, very carefully." The test program began on March 16, 1944, with 2 Corsairs, 1 pilot, and enough altitude to make mistakes survivable. Morrison had convinced Major Harold Bauer, VMF 215's commanding officer, that Blackburn's throttle technique deserved systematic evaluation. Bauer was skeptical but practical. If American pilots were dying because dive recovery procedures were wrong, he wanted to know before he lost more men to what everyone assumed was pilot error or bad luck. They picked Lieutenant Thomas Wade for the test flights. Wade was 24 years old, had logged 340 hours in the Corsair, and possessed the kind of mechanical intuition that made him dangerous in good ways. He understood how aircraft worked at a level most pilots never reached. More importantly, he was calm under pressure. The kind of pilot who could run controlled experiments at 400 miles per hour while remembering to note manifold pressure readings and control stick forces. The test protocol was simple in concept, terrifying in execution. Wade would climb to 25,000 feet over open ocean east of Treasury Islands. He'd establish a 70-degree dive, accelerate to 400 miles per hour indicated airspeed, then execute recovery using 2 different techniques. First attempt would follow standard procedures: maintain full power, pull back on the stick with maximum force, recover as quickly as possible. Second attempt would use Blackburn's technique: reduce throttle to idle, wait 2 seconds, then initiate recovery pull. Morrison would fly chase in a second Corsair, maintaining visual contact and documenting what happened. They launched at 0600 hours on March 16th, into clear skies and calm air. Wade climbed to 25,000 feet, positioned himself over empty ocean, and pushed over into his first test dive. Morrison stayed high, watching Wade's Corsair angle downward and accelerate. At 20,000 feet, Wade's aircraft was doing 300 miles per hour. At 15,000 feet, 360. At 12,000 feet, he was approaching 400 miles per hour and beginning his recovery. Standard technique. Full power. Maximum back pressure on the stick. Morrison watched Wade's Corsair begin to level off, but the recovery arc was enormous. Wade started his pull at 12,000 feet and finally achieved level flight at 6,000 feet. 6,000 feet of altitude, consumed in recovery. Morrison noted the numbers, then watched Wade climb back to 25,000 feet for the second test. The second dive looked identical until 12,000 feet. Wade's Corsair reached 400 miles per hour, indicated, and Morrison saw the nose attitude change slightly as Wade reduced throttle. The propeller note changed, audible even from Morrison's position, 1,000 feet away. The Corsair's descent continued, but the quality of the dive looked different, cleaner somehow, less violent. At 10,000 feet, Wade initiated his recovery pull. The Corsair's nose came up smoothly, progressively. Level flight at 7,500 feet. Only 4,500 feet of altitude consumed, 1,500 feet less than the standard technique recovery. They ran 6 more test profiles that morning. Every single iteration showed the same pattern. Throttle reduction during high-speed dives resulted in recoveries that required less altitude, produced smoother control response, and subjected the airframe to lower G-loads. Wade reported after landing that control stick forces during throttle-reduced recoveries felt 30 to 40% lighter than standard technique recoveries, at the same airspeed. Morrison spent the afternoon doing math that should have been done in Connecticut before the Corsair ever reached production. The physics were straightforward once you looked at them correctly. At 400 miles per hour, the Corsair's 3-bladed propeller, spinning at 2,700 RPM, was moving its blade tips through the air at approximately 850 feet per second. The speed of sound at sea level was roughly 1,100 feet per second. The propeller tips were operating at about 77% of Mach 1, deep into the transonic regime, where airflow became turbulent and unpredictable. That turbulent airflow behind the propeller disc was striking the Corsair's fuselage, creating drag and disrupting the smooth flow over the wings and tail surfaces. The disrupted airflow reduced the effectiveness of the elevator and rudder, making control inputs less effective. The pilot had to pull harder to get the same response. The harder pull required more time. More time meant more altitude consumed during recovery. Reduce the throttle to idle, and propeller RPM dropped to around 1,800. Blade tip speed decreased to approximately 550 feet per second, only 50% of Mach 1. The propeller transitioned from generating turbulent transonic flow to producing relatively clean subsonic flow. The airflow behind the propeller disc smoothed out. The disruption to the fuselage decreased. The elevator and rudder regained effectiveness. Control inputs produced better responses with less force required. Recovery became quicker and required less altitude. The solution was absurdly simple. It violated every instinct pilots had been trained to follow, but it worked. And if it worked for Corsairs diving at 400 miles per hour, it might work even better at higher speeds, where compressibility effects became more severe. Morrison wrote up his findings in a 5-page report that night and handed it to Major Bauer the next morning. Bauer read it twice, called Blackburn and Wade into his office, and asked the question that would define how this information spread through the fleet. If this technique works, why didn't Vought figure it out during testing? They've got engineers. They've got test pilots. They've got wind tunnels. How did we discover this in combat when they should have found it in Connecticut? Wade answered. Because they tested at altitudes where we're supposed to fight, not altitudes where we actually fight. And they probably tested recovery procedures at speeds where the aircraft was still controllable using normal techniques. Nobody was testing emergency recoveries from maximum speed dives, because those situations aren't supposed to happen if you fly according to the manual. But they do happen, Bauer said. Every day, Wade replied. And pilots die because we're using recovery techniques that work fine at 300 miles per hour but fall apart at 400. Bauer made his decision. We're teaching this to every pilot in the squadron. Today. And I'm sending Morrison's report up the chain with a recommendation that this becomes standard doctrine for all Corsair units. He looked at Blackburn. You almost died finding this. We're going to make sure other pilots don't have to learn it the same way. VMF 2-15 held emergency training sessions on March 17th and 18th. Every pilot flew practice dives with Morrison or Wade acting as instructor. The technique was simple enough that most pilots mastered it within 2 or 3 attempts. The psychological barrier was harder to overcome than the physical technique. Pilots had been trained for months to maintain power during dives. Their instinct when things got dangerous was to add power, not reduce it. Breaking that instinct required practice and trust. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By March 20th, all 18 pilots in VMF 215 could demonstrate throttle-reduced dive recoveries. More importantly, they understood why it worked. Morrison had explained the aerodynamics clearly enough that pilots could visualize what was happening to airflow over their aircraft at high speeds. Understanding the mechanism made them more confident in using the technique under actual combat stress. The combat test came on March 23 during an escort mission, protecting SBD Dauntless dive bombers attacking Japanese shipping at Rabaul. 8 Corsairs from VMF 215 were flying high cover at 20,000 feet when 12 Zeros climbed from below to intercept the bombers. Lieutenant Wade led 4 Corsairs down in a slashing attack, diving from altitude to build speed before engaging. He entered the dive at 280 miles per hour, accelerated to 400 bar, 20 by 18,000 feet, and flashed through the Zero formation at a closing speed that gave Japanese pilots maybe 2 seconds to react. Wade fired a 3-second burst at the nearest Zero, saw hits sparkle along its fuselage, then continued his dive. Standard Corsair tactic. 1 pass at high speed, then extend away and climb back to altitude using superior power. Except this time, 2 Zeros rolled and followed him down. They couldn't match his dive speed, but they stayed in visual contact, diving at their maximum safe velocity. Wade's airspeed indicator was showing 440 miles per hour at 15,000 feet. He should have been pulling away, opening distance, leaving the Zeros behind. Instead, they were maintaining pursuit geometry, staying in the fight. Wade realized what was happening. The Zeros weren't trying to catch him in the dive. They were betting he'd have to pull out eventually, and when he did, they'd be close enough to engage during his recovery when his aircraft was slow and vulnerable. It was a smart tactics. It was exactly what American intelligence said Japanese pilots couldn't do, and it would have worked a week earlier. At 12,000 feet, Wade reduced his throttle to idle. His Corsair's propeller note dropped. The dive continued, still building speed. 450 miles per hour, 460. He was approaching speeds where most pilots would be feeling the first hints of compressibility buffeting. At 10,000 feet, he pulled back on the stick. The response was immediate and smooth. The nose came up steadily. Level flight at 7,000 feet, still carrying 440 miles per hour in straight and level flight. The 2 Zeros were still diving, committed to their pursuit geometry, expecting Wade to be much lower when they completed their own recovery. Instead, Wade was level at 7,000 feet, already bringing his throttle back to combat power, already beginning a climbing turn to reposition. The Zeros pulled out at 5,000 feet, bleeding speed in their recovery, and found themselves below and behind a Corsair that was accelerating and climbing. Wade reversed, dove on the nearest Zero, and fired a 4-second burst that tore the Zero's wing off at the root. The second Zero broke hard, dove for the deck, and escaped. Wade returned to Treasury with 1 confirmed kill and a combat report that described using throttle reduction for both dive recovery and tactical positioning. The after-action review that evening attracted pilots from every Corsair squadron on the island. Word was spreading that VMF 215 had developed a new dive technique. Pilots wanted to know if it was real or just another tactical rumor that would evaporate under actual combat conditions. Major Bauer demonstrated it the next day during a training flight, with observers from VMF 221 and VMF 122. He climbed to 25,000 feet, rolled into a dive, accelerated to 450 miles per hour, reduced throttle to idle, and recovered at 8,000 feet with control inputs that looked effortless from the chase aircraft's perspective. Then he did it again at 470 miles per hour, recovering at 9,000 feet with the same smooth control response. The observers returned to their squadrons and started their own test programs. Within 2 weeks, 3 Marine Corsair squadrons in the Treasury and Green Islands area were teaching throttle-reduced dive recovery as standard procedure. The technique spread from squadron to squadron through pilot conversations and informal demonstrations. No official training bulletin. No directive from headquarters. Just combat pilots sharing information that kept them alive. The Navy's Bureau of Aeronautics learned about the throttle reduction technique in early April when a routine maintenance report from Treasury Island mentioned that pilots were using non-standard dive recovery procedures. The report triggered an investigation. By April 12th, a technical team from BUAir had arrived at Treasury to evaluate what they initially assumed was dangerous field innovation that violated approved flight procedures. Commander Walter Pierce led the investigation team. He was 42 years old, an academy graduate, and a former test pilot who'd helped develop carrier landing procedures in the 1930s. He arrived expecting to find reckless pilots doing stupid things with expensive aircraft. What he found instead was systematic testing, documented performance data, and combat results that suggested VART's original dive recovery procedures were inadequate for high-speed combat conditions. Pierce flew with Wade on April 14th. They climbed to 25,000 feet, and Wade demonstrated both standard and throttle-reduced recovery techniques at 400 miles per hour. Pierce flew the second demonstration himself, carefully noting control forces, recovery altitude, and aircraft response characteristics. After landing, he spent 3 hours reviewing Morrison's analysis and examining the math behind propeller blade tip velocities at high RPM. His report to BUAir, dated April 18, 1944, acknowledged that field-developed throttle reduction techniques produced measurable improvements in high-speed dive recovery performance. The report recommended immediate engineering analysis of the technique and consideration for inclusion in standard Corsair operating procedures. More significantly, Pierce recommended that VART conduct wind tunnel testing to understand why their original dive procedures were less effective than techniques developed by combat pilots. VART's response arrived on May 2nd. The engineering team at Stratford had run computational analysis on propeller performance at high airspeeds and high RPM. Their calculations confirmed what Morrison had worked out with a slide rule in a tent on Treasury Island. At airspeeds above 400 miles per hour, the Corsair's propeller operating at full power RPM was generating significant turbulent flow that degraded control surface effectiveness. Reducing RPM improved airflow characteristics and enhanced control response. The engineering report included a somewhat defensive explanation for why this hadn't been discovered during original testing. VART's test protocols had focused on measuring maximum dive speed and structural limits, not optimizing recovery procedures at various throttle settings. The assumption had been that maintaining power during dives was always preferable. That assumption was based on conventional wisdom and earlier aircraft designs, where propeller blade tip speeds didn't approach transonic velocities. The Corsair was fast enough and powerful enough that its propeller could create problems earlier aircraft hadn't encountered. VART's engineers had designed a fighter that could dive faster than their testing protocols anticipated. Combat pilots had discovered the limitation and developed a workaround before engineers realized the problem existed. On May 24, 1944, the Navy issued a formal training bulletin to all Pacific Fleet fighter squadrons operating F4U Corsairs. The bulletin, designated NAVAIR Training Circular 14-44, officially recognized throttle-reduced dive recovery as an approved technique for high-speed emergency situations. The circular included specific guidance. Reduce throttle to idle or near idle when airspeed exceeds 400 miles per hour in dives steeper than 60 degrees. Maintain reduced power until recovery is initiated. Restore full power after achieving level flight or controlled climb. The circular specifically credited field observations and testing by Marine Fighter Squadron 215 for identifying the technique and developing training protocols. Blackburn's name appeared in the acknowledgement section, along with Wade's and Morrison's. It was unusual recognition in a system that typically absorbed field innovations without crediting the individuals who developed them. The technique propagated through the Pacific Fleet during summer 1944. Every Corsair squadron received the training circular. Most conducted their own verification flights before adopting the technique as standard procedure. The results were consistent. Pilots reported improved control response during high-speed recoveries, reduced altitude loss, and increased confidence in their aircraft's dive performance. The tactical implications were significant. Corsair pilots had always known they could outdive Japanese fighters. Now they could recover from those dives more quickly and at higher altitudes, which meant they could re-enter combat faster instead of spending time climbing back to fighting altitude. The dive became not just an escape maneuver but an offensive weapon. Dive on an enemy, make your attack, recover quickly, and position for a second pass before the enemy could react. Japanese pilots noticed the change. Intelligence reports from captured documents and interrogated prisoners indicated that by mid-1944, Japanese fighter doctrine had shifted to avoid vertical engagements with American fighters whenever possible. The previous assumption that American aircraft had to commit significant altitude to dive attacks was no longer valid. Corsairs and Hellcats were recovering faster and repositioning more aggressively than Japanese tactical planning anticipated. The kill ratios reflected the tactical shift. Corsair squadrons that had been posting 2-to-1 or 3-to-1 victory ratios in early 1944 were achieving 6-to-1 and 8-to-1 ratios by summer. Some of that improvement came from declining Japanese pilot quality, as experienced aviators were killed and replaced with poorly trained recruits. But the dive performance advantage was a multiplier that made everything else more effective. Lieutenant Commander Blackburn flew his last combat mission on September 3, 1944. He'd logged 106 combat missions, scored 11 confirmed aerial victories, and survived situations that should have killed him multiple times. His discovery of the throttle reduction technique wasn't the reason he survived, but it was one of many small tactical advantages that tilted probability in favor of American pilots who were flying aircraft with performance characteristics their designers hadn't fully understood. After the war, Blackburn rarely discussed the throttle technique. In a 1963 interview for a Navy historical project, he described it as something I did without thinking that turned out to matter. He was more interested in talking about the men he'd flown with, the ones who didn't make it home, the pilots who died, learning lessons that survivors got to apply. The technique became standard curriculum at operational training units by late 1944. New pilots arriving in the Pacific already knew how to reduce throttle during high-speed dives. It was just another procedure, like trimming for cruise or setting mixture for altitude. The combat innovation became routine training, which is how successful field developments are supposed to evolve. Vought incorporated the throttle reduction guidance into F4U flight manuals, starting with the -4 variant in 1945. The manual section on high-speed flight characteristics explicitly described propeller, blade tip, compressibility effects, and recommended power reduction during dives exceeding 400 miles per hour indicated airspeed. What had been a violation of procedures in March 1944 became official operating guidance by March 1945. The principles survived the transition to jet aircraft. Early jets didn't have propellers, but they had their own compressibility problems. Test pilots and combat aviators continued discovering that emergency procedures written by engineers in safe facilities sometimes needed modification by people who actually used the equipment under stress. The distance between theoretical performance and combat reality remained significant. The bureaucratic challenge was creating systems flexible enough to incorporate field innovations without crushing them under safety regulations and liability concerns. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.